Cracks in concrete structures must be properly filled to restore integrity and durability. The European standard EN 1504 Part 5 provides a framework for crack injection materials, ensuring they meet defined performance criteria for different crack repair needs. This time will outline the types of crack filling materials according to EN 1504-5 and their applications, focusing on structural bonding, limited flexible filling, and swelling materials. We will also discuss application methods, mechanical packers, surface packers, and impregnation, key material properties under the standard, and best practices for selecting the right material based on crack type and conditions. The aim is to deliver a clear, technical overview for engineers, contractors, and sales professionals involved in concrete repair. EN 1504 Part 5 is part of the EN 1504 series on the protection and repair of concrete structures, and it specifically deals with concrete injection products. It defines three main categories of crack filling injections. 1. Force transmitting filling. Category F injection materials that structurally bond cracks, essentially restoring the load-bearing capacity. 2. Ductile filling. Category D injection materials that remain flexible to accommodate limited movement. 3. Swelling fitted filling. Category S materials that swell to seal cracks, especially against water ingress. Each category has specific performance requirements. For example, structural, force transmitting products must achieve high bond strength to concrete, whereas flexible ones must maintain a waterproof seal under pressure without cracking. EN 1504 Part 5 ensures that products are tested and CE marked to meet these criteria, giving engineers confidence that a chosen crack filler will perform as expected in terms of strength, adhesion, and durability. Chapter: Types of Crack Filling Materials, EN 1504 Part 5 Categories. Structural bonding materials, force transmitting, Category F. Structural crack filling materials are used when cracks are load-bearing or need to restore structural continuity. Typically, these are low-viscosity, solvent-free epoxy injection resins designed for high-strength bonding. Their excellent flow allows injection into cracks as narrow as about 0.1 millimeters, penetrating the fine network of the crack. Once cured, epoxies have high adhesive tensile strength, often more than 2 megapascal as per EN 1504 Part 5 F1 category, and high inherent strength. This means they durably reestablish the structural bond of the cracked concrete, restoring it to act monolithically, continuous under loads. In practice, using a structural injection resin like an epoxy will glue the crack faces together, effectively making the concrete element whole again. Some specialized polyurethane resins can also achieve structural strength bonding, but epoxies are the most common choice for force-transmitting repairs due to their rigidity and high compressive tensile properties. Limited flexible filling materials, ductile, Category D. When cracks are subject to slight movements from thermal expansion, shrinkage, or cyclic loading, and a rigid repair would recrack, flexible crack filling materials are recommended. These are often polyurethane injection resins formulated to have some elasticity or to form a microcellular structure. According to EN 1504 Part 5 Category D requirements, the injected material must not fracture when the crack faces move slightly. In practical terms, limited flexibility resins bond to the crack flanks, but can tolerate small expansions or contractions of the crack without losing adhesion. For example, certain PU resins react with a bit of water to form fine bubbles, foam structures, that can compress or stretch slightly. This limited flexibility bridges minor crack width changes due to temperature change or live loads, preventing the cracks from reopening. Flexible injection materials are also typically waterproof, providing an elastic seal. EN 1504 Part 5 classifies them by their water tightness. For example, D1 for materials watertight up to 2 × 10 to the power of 5 Pa of water pressure. These materials are used when the goal is more to seal the crack and accommodate movement than to add structural strength, for instance, in non-structural shrinkage cracks or cracks in elements that experience slight movements. Swelling fitted filling materials, Category S. Swelling fitted crack filling materials are used primarily for watertight sealing of cracks, joints, or voids, especially in the presence of moisture. These materials are typically hydrophilic resins or gels that expand in volume when they contact water. A common example is an acrylate gel, an elastic, very low viscosity resin that can penetrate extremely fine cracks and pore structures. Upon injection, acrylate and similar gels remain gel-like and flexible, and if water tries to leak in, the material swells to block the passage. This makes them excellent for waterproofing cracks in basement walls, tunnels, or other water-retaining structures. They also have adjustable reaction, setting, times, allowing the installer to tailor how fast they gel after injection, useful for adapting to site temperature or crack complexity. Category S materials may not add structural strength, but they ensure a permanent seal against water and contaminants, like chlorides from de-icing salts, penetrating through cracks. In summary, swelling injection materials are chosen when stopping water ingress is the main objective. They often work in tandem with flexible resins. For example, a hydrophilic polyurethane that foams and swells can both seal a leak and remain slightly flexible. Proper application is as important as material selection. Yen 1504 Part 5 does not prescribe how to inject, but best practices have evolved to effectively get the material into the crack. The main application methods are injection via mechanical packers, injection via surface packers, and crack impregnation. Each method suits different situations. Mechanical packers, drilled injection. This is the most common method for structural crack injection. It involves drilling small diameter holes at regular intervals along the crack path and installing mechanical packers, injection ports, into these holes. Typically, holes are drilled at a 45 degrees angle, alternating sides of the crack, so that they intersect the crack roughly at mid-thickness of the concrete element. The spacing of packers depends on the crack width and member thickness, often roughly 1/2 the thickness of the concrete member apart. Mechanical packers have rubber sleeves that expand as they are tightened, creating a seal in the drilled hole. Once installed, they allow injection under pressure directly into the crack depth. This method supports high injection pressures to drive resin into fine fissures or long cracks, and ensures the full depth of a thick structural element is treated. It is ideal for structural epoxy injections. After injection, packers can be removed and the drill holes patched. Surface packers, surface ports when drilling is undesirable or impossible. For example, in pre-stressed concrete elements, thin concrete sections, or architecturally sensitive surfaces, surface packers are used. Surface packers are small port nipples that are glued directly over the crack on the surface using a strong epoxy paste. The rest of the visible crack is also sealed with the same epoxy paste except the port openings. Once the epoxy paste has hardened, the crack becomes a closed conduit and resin is injected through the surface packers. The spacing of surface packers is usually similar to the member thickness. They're placed closer together than drilled ports because resin must travel within the crack from port to port. Surface injection is done at lower pressure compared to mechanical packers to avoid dislodging the surface ports or the epoxy seal, but it can effectively fill cracks in cases where drilling could damage reinforcement or where backside access is limited. This method is commonly used for narrower cracks in walls or slabs where drilling holes might not go through, or in repair of historical structures to avoid drilling. Impregnation. Gravity-fed filling crack impregnation is a low-pressure or pressure-less method for fine, shallow cracks and surface crack allure, a network of hairline surface cracks. In this technique, a low-viscosity resin is introduced on the surface and allowed to penetrate by gravity and capillary action into the cracks. It is most suitable for horizontal or gently sloping surfaces, such as floor slabs or decks, where the resin can be pawned or repeatedly applied over the crack path. The resin's wetting ability is crucial. It must slowly soak into the tiny cracks. Over time, the cracks fill and the resin cures in place, sealing the surface. This method does not use injection pressure, hence it is limited to relatively thin sections or surface cracks. The effectiveness depends on penetration depth, which in turn depends on crack width and resin viscosity. Impregnation is a good solution for structural or non-structural hairline cracks that only need to be sealed to prevent ingress of water or chemicals. It's also used as a finishing step after pressure injection to fill any remaining surface voids. However, because it may not reach deep or through thickness cracks, it's not relied on for ideal structural repairs, but rather for surface sealing. Material choice for movement joint filling. The materials used to fill movement joints must remain flexible or accommodating of movement once cured. Rigid resins like standard epoxies are generally unsuitable here. They would create a stiff plug that could crack or debond when the joint opens or shifts. Instead, elastic injection resins and swelling materials are the preferred choice for movement joints. EN 1504 Part 5 classifies certain injection products for non-structural, sealing purposes, including those with elongation capability, often termed flexible fillers. According to industry guidance, elastic acrylate gels are particularly suitable for joints that experience movement. These materials cure into a rubbery and gel-like that can compress or elongate slightly as the joint moves, thus maintaining the seal. Acrylate gels. Acrylate injection gels are another top choice for movement joints, especially in underground structures and tunnels. Acrylate resins are very low viscosity, almost like water, allowing them to infiltrate fine joint gaps or surrounding soil before gelling. They are typically injected as two-component systems. The components mix and then polymerize into a gel. The key advantage of acrylate gels is their combination of flexibility and hydrophilicity. Once cured, an acrylate gel stays rubbery and can accommodate joint movements, and it also exhibits pronounced hydrophilic swelling. In contact with water, the cured acrylate will absorb some water and swell, enhancing its sealing performance. If the joint dries, some acrylate gels can shrink slightly, but upon re-wetting they swell back. This reversible swelling ensures a long-term seal even with wet-dry cycles. Because of these traits, acrylate gels are often used for post-construction joint sealing in tunnels. They can form an elastic waterproof membrane within the joint or even a curtain just behind a joint if injected beyond the lining to block water ingress. For example, if an original segment gasket or water stop are failing, engineers might inject acrylate gel to backfill the joint gap behind the gasket or water stop. The acrylate gel will flow into any voids and harden into a gel that both adheres and wedges itself in place, stopping the leak while remaining flexible as segments move. Additionally, acrylates have adjustable set times. For long joints, a slower gel time might be used to ensure the material propagates the length of the joint before gelling. Acrylate gels and PU gels are sometimes used in tandem. A fast foaming PU can initially stop a high flow leak. Then a slower acrylate gel is injected to permanently seal the joint and fill any remaining cavities. This two-step approach is common in waterproofing practice, though the specifics depend on site conditions. Application methods for movement joint filling. Movement joints, such as expansion joints in concrete structures or segment joints in tunnels, present a unique challenge for sealing and injection. These joints are designed to accommodate structural movements, expansion, contraction, or settlement, so any repair or injection material must seal the joint against leaks while allowing continued movement. In tunnel segmental linings, for example, precast concrete segments fit together with gaskets at the joints. Over time or under high water pressure, these joints can begin leaking. Similarly, in above-ground concrete structures, expansion joints may leak if the water stop or sealant fails. This chapter discusses the appropriate methods to fill and seal movement joints, focusing on injection techniques and material choices that maintain flexibility. Sealing and injection techniques for movement joints. When addressing a leaking movement joint, the repair method must avoid locking the joint. In practice, this means injecting flexible sealing materials into or behind the joint rather than using rigid fillers. A common technique in tunnels is to drill injection holes along the joint and inject a grout that travels into the joint gap or behind the original gasket. For instance, in segmental tunnel lining, holes can be drilled directly through the segment concrete to intersect the joint at intervals, often alternating sides along the joint. Packers are installed in these holes, and a low-viscosity resin is injected into the joint area. It is crucial to use relatively low injection pressures in this process so as not to damage or dislodge any existing joint gasket or filler. The gasket itself often serves as a boundary to contain the injected grout. The goal is to fill the annular gap or any voids around the joint on the external, water-facing, side, effectively creating a new water barrier. In tunnel repairs, a specialized method involves drilling through the gasket with a thin injection needle, then injecting grout on the water side of the gasket. This targets the leak at its source and minimizes drilling through structural concrete. In all these techniques, the spacing of injection points is planned to ensure complete coverage. As a rule of thumb, movement joint injections might use packer spacings on the order of 20, 50 cm, but this can vary with joint size and leak severity. An alternating pattern, staggered on either side of the joint for through drilling methods, helps the resin cover the full joint width. After injection, any drilled holes are typically sealed off, for example, with packers left in place or with hydraulic mortar once removal to prevent water or grout egress. It's worth noting that unlike rigid crack injection, the injected material in a movement joint is not intended to restore structural continuity. The joint is meant to move. Instead, it creates a waterproof but flexible plug or curtain around the joint. As such, pressure injection is carefully controlled, just enough to fill voids and saturate the joint's vicinity, but kept below the lift-off pressure that could overcome the joint's compressive seal. Suitable injection pumps. Successful crack injection not only depends on the right material, but also on using suitable pumping equipment. Injection pumps must be chosen based on the resin type, required pressure, and practicality on site. There are essentially 3 categories of injection pumps: single-component pumps and 2-component, fixed ratio, pumps, each suited to different materials and job sizes. Below is a comparison of these pump types in terms of efficiency, material compatibility, and ease of use. Single-component pumps. These pumps, often piston or diaphragm type, handle one material at a time, making them simple and versatile. They are commonly used for most one-component polyurethane injections, especially hydrophobic PU foams and certain pre-mixed epoxies. Single-component pumps can generate high pressures, often more than 100 bar or 1,500 psi, to push resin into fine cracks. They typically have straightforward operation and maintenance. For example, cleaning is done by flushing with a suitable solvent or water, depending on the resin. However, when using fast-curing materials, the resin's pellet life must be monitored carefully if the pump does not mix components automatically. In general, single-component pumps are efficient for small to medium jobs and are valued for their portability and ease of setup. Hand-operated models exist for small-scale injections, though electric or pneumatic dries are preferred for consistent pressure and higher volume. The choice often depends on project size. A manual hand pump might suffice for a minor repair, whereas an electric/pneumatic pump can save considerable time and labor on larger jobs. Additionally, piston versus diaphragm pumps is a consideration in pump selection. Piston pumps can achieve very high pressure and are suitable for high-viscosity resins, like some epoxies, or when injecting into very tight cracks. Diaphragm pumps, on the other hand, offer smoother, pulsation-free flow and excellent chemical compatibility. They are often used for lower viscosity resins and in applications where moderate, steady pressure is sufficient. In practice, modern single-component electric pumps might use piston mechanisms for high-pressure needs or diaphragm mechanisms for ease of maintenance, each type balancing efficiency and where depending on the material pumped. Two-component pumps. Two-component injection pumps are designed to simultaneously handle and mix 2 separate components, resin and hardener, just before or at the point of injection. This ensures consistent mix quality and avoids premature curing pot life issues in the pump or lines. Two-component pumps are mandatory for very fast-reacting systems such as acrylate gels. Acrylate injection gels have extremely low viscosity and short reaction times, adjustable from seconds to minutes, so the components must be kept separate until they reach a static mixer in the injection head. A typical setup uses 2 feed lines, one for each component, leading to a static mixing nozzle where the resin is mixed just as it is injected. Because acrylate gels cure to a flexible gel quickly, these pumps often include a flushing system. For instance, a water flush pump to immediately clean out the mixing head and hoses after injection. In terms of efficiency, two-component pumps allow continuous injection of large volumes without stopping for batch mixing, which is ideal for big jobs or when a long section of crack/joint must be injected in one go. They are generally powered by air compressors or electric motors and built with corrosion-resistant parts, like stainless steel, to handle reactive resins. While two-component pumps are more complex, requiring setup of dual hoses, mixer, and flush, and typically heavier, their ability to process fast-curing materials efficiently makes them indispensable for certain injections. Ease of use comes with training. Operators must understand the mixing ratio settings and maintenance, like cleaning static mixers, etc., but modern two-component pumps are engineered to simplify these tasks, often with disposable mixers and quick flush features. Efficiency and usability considerations. The efficiency of an injection pump is measured by how reliably it delivers the required pressure and flow of resin with minimal downtime. Powered pumps, electric or pneumatic, generally allow faster injection rates and sustained pressure compared to manual hand pumps, which can be labor-intensive and slow. On large projects, the higher upfront cost of a quality electric or pneumatic pump is often offset by significant time and labor savings through more efficient injection progress. Material compatibility is also critical. Pumps in contact with aggressive resins, like acrylic components, should be made of stainless steel or other non-corroding materials to withstand chemical exposure. Likewise, the pump's hose and seal materials must resist the resin. For example, epoxies can be solvent-cleaned but may attack certain plastics, so hoses must be chosen accordingly. Ease of use also ties into cleanup and maintenance. Pumps used with quick-curing resins, like acrylate or fast-set PU, must be cleaned immediately and thoroughly after use. Features like built-in flush pumps or easy disassembly of mixers greatly aid in this. Simpler one-component pumps usually just require flushing the lines with solvent or cleaner after injecting epoxies or polyurethanes, which is relatively straightforward. In summary, selecting the right pump type ensures that the crack-filling material can be injected efficiently and safely. A well-chosen pump, matched to the resin's characteristics, will deliver consistent results and be user-friendly for the injection crew, whereas an improper pump could lead to clogs, inadequate pressure, or premature curing and ultimately compromise the repair. Key material properties and performance criteria of EN 1504 Part 5. EN 1504 Part 5 sets out specific performance criteria for crack injection materials to ensure they are fit for purpose. Some of the key properties and requirements under this standard include adhesive tensile strength for structural injection products. The bonds to concrete, measured as adhesive tensile strength, must meet minimum values. Category F materials need high strength. For example, F1 class requires at least 2 megapascal bond strength to concrete. This ensures the injected material can transmit forces across the crack without debonding. In practice, structural epoxies often far exceed this value, providing excellent adhesion that can even exceed the tensile strength of concrete itself. Flexibility and water tightness. For flexible sealing materials, performance is measured by their ability to remain watertight under pressure and accommodate movement. EN 1504 Part 5 defines classes like D1 and D2 based on a water pressure test. For example, D1 must resist water ingress at up to 2 times 10 to the power of 5 Pa pressure. These materials are not primarily load-bearing, so instead of bond strength, their key criterion is that they do not crack or leak when the crack opens slightly or when water tries to push through. They are typically tested for elasticity and sealing up to a certain crack width and pressure. Crack width penetration capability. Injection products are classified by the crack width range they can effectively fill. The standard uses a designation W1, W2, W3, etc., where the number is the crack width in tenths of millimeters that the product can penetrate. For example, W2 denotes a product suitable for 0.2 millimeters cracks, W5 for 0.5 millimeters, and so on. A lower number indicates a lower viscosity, more fluid, resin capable of entering finer cracks. Engineers should ensure the chosen material's W rating matches the estimated crack widths. A high viscosity resin might not fill a hairline crack. Moisture compatibility. Cracks can be dry, damp, wet, or actively water-bearing. EN 1504 Part 5 classifies products by the moisture condition they are suited for. 1 equals dry, 2 equals damp, 3 equals wet, 4 equals water flow. For example, many epoxies are only suited for dry to slightly damp cracks, while polyurethanes can often work in wet or even water flow conditions. The product's documentation will state the allowable moisture condition. It's critical to use a material that can properly cure in the actual field conditions. Otherwise, adhesion or curing may be compromised. Durability and other properties. The standard also covers durability aspects such as resistance to chemicals, thermal expansion behavior, and aging. Bit crack fillers should be non-shrinking or slight expansion for swelling tights, non-corrosive to reinforcement, and stable over time. Viscosity, usually given in MPa-S, is an important parameter provided by manufacturers, as it indicates how easily the resin can flow into cracks of a given width. Pot life and curing time are specified for different temperatures to ensure the material can be injected before it starts to gel. For swelling materials, Category S, the expansion ratio and the ability to sustain multiple wet-dry cycles without performance loss are key parameters. Manufacturers will declare these values in accordance with the standard testing. Selecting an appropriate crack injection material influences a successful repair. The engineer or contractor should evaluate the crack characteristics and service conditions, then choose a material and method that aligns with EN 1504 Part 5 category requirements and the project goals. Here are some best practice considerations. Determine the crack's nature, structural or non-structural. Understand whether the crack affects structural capacity. If the crack is in a load-bearing area and is essentially a break in the concrete structural continuity, for example, a crack in a beam, column, or foundation that opens due to overload or settlement, a structural injection, Category F, is needed. A high-strength epoxy resin is appropriate to restore the load transfer across the crack. If the crack is mainly due to shrinkage or temperature effects and does not threaten structural safety, you may prioritize sealing over strength. Assess crack movement. If the crack is active or may move in the future due to temperature changes, cyclic loads, creep, etc., our rigid filler might crack again. For such cases, choose a limited flexibility resin, Category D, that can accommodate small movements. For example, a slightly flexible polyurethane will stay intact if the crack width varies a bit with seasons or loading, thereby maintaining a seal. Structural cracks that are subject to minor movement can sometimes be injected with a combination of materials, but generally, do not use a purely rigid epoxy in a known moving joint, or it may fail again. Consider the presence of water. For damp or wet cracks, ensure the product is suitable for those conditions. Many polyurethane-based systems can cure in the presence of water and even use water to trigger reaction, whereas standard epoxies require mostly dry conditions. If a crack is actively leaking water, for example water under pressure seeping through a crack in a basement or tunnel, it is often best to employ a two-stage injection. First, use a fast-foaming PU resin to temporarily stop or slow the water flow. Then inject a second resin, either a non-foaming flexible resin or an epoxy if structural strength is needed, to permanently fill and seal the crack. Hydrophilic swelling resins, Category S, are particularly useful for water-bearing cracks. They will foam or swell on contact with water to ensure a tight seal. Always check the product's classification for moisture condition, for example, rated for wet or water-bearing cracks, before use. Match the resin viscosity to crack width. Measure or estimate the crack width or range of widths. Fine hairline cracks, less than 0.2 millimeters, require very low viscosity injections. For instance, specialty epoxies or acrylate gels that can penetrate those micro cracks. Using a too viscous material on a tiny crack will result in poor penetration and an incomplete fill. Conversely, very wide cracks or voids might waste an expensive low viscosity resin. For widths above a few millimeters, Sometimes a filler or thicker resin, or even a cementitious grout, if appropriate, might be more economical. The N1504 Part 5's W classification is a useful guide. Ensure the product's W rating, for example W1, 40.1 millimeters, W5, 40.5 millimeters, covers the smallest crack you need to inject. Account for temperature and cure time. Consider the ambient and substrate temperature during injection. Each resin has an application temperature range. For example, usable between 5 and 30 degrees centigrade is common in consideration to the reactability of chemicals and the application condition of environments. And the viscosity and reaction time can change with temperature. In cold weather, choose a formulation or accelerator that can still flow and cure in reasonable time. Also, plan the workable pot life. For large cracks or many ports, a longer pot life resin may be needed to avoid it setting in the line or packer. Ensure the cure schedule fits within the project timeline so that the structure can be returned to service as needed. The reaction time of the resin is influenced by the temperature of both the material and the structure. Higher temperatures will accelerate the curing process, while lower temperatures will slow it down. Moreover, the maximum injection pressure equals concrete compressive strength divided by 3 times 10 bar. In conclusion, EN 1504 Part 5 provides a vital technical standard for crack injection materials, ensuring that products used for filling cracks in concrete are up to the job whether the goal is structural repair or leak sealing. We have discussed the 3 main types of crack filling materials: structural bonding resins for restoring strength, flexible filling resins for accommodating movement, and swelling materials for water sealing. We also reviewed the proper methods of injection, from mechanical packers to surface ports and impregnation, that deliver these materials into cracks effectively. Key performance criteria such as bond strength, flexibility, crack penetration ability, and durability were highlighted as the benchmarks that EN 1504 Part 5 compliant products must meet. When selecting a crack injection solution, always consider the crack's characteristics and service conditions to choose the appropriate material category and application technique. A static structural crack calls for a different approach than moving, leaking crack. By following the guidelines of EN 1504 Part 5 and the best practices outlined, engineers and contractors can ensure that the repaired crack will not only be filled, but that it will stay filled and functional under the structure's future loads and environmental exposure. In a word, using the right crack filling material and method results in safer, more durable concrete repairs, which is the ultimate goal for all stakeholders, from designers to contractors and product suppliers. The clarity and rigor of EN 1504 Part 5 help us achieve that goal by matching the right material to the right crack every time.